Okay, now here's the good part about indicators and how they change color. When the color starts to change, when there's about 10% of one of the colors, your eyes are going to be able to detect it. You still see the original color, but you're going to start to see the other color coming in. When there's about 10% of the base. So during the titration, you're adding base, adding base, adding base. You're taking some of the hydrogens off of this. When you get to about 10% of that and 90% of that, then the color starts to be different. At the beginning, it was all yellow. All you see is yellow. But then when you got about 10% of this, then you start to see the color. Now, what color would you see? You're going to have 90% yellow, 10% blue. What color would you get?
Green.
It's going to be a green color. What about when you have 80%, 20%?
Green.
It's still going to be green. Will it be the same green?
No.
No, it's going to be green with more blue in it. Are you with me? So you're going to have this transition of color, but you'll start that transition at about 10%. So at 10%, that means, now this is not, it's actually about 1 to 9, because 10% and 90% is more like 1 over 9. But just to have round numbers, and you'll see books always do this, they don't go exactly, because, I mean, this says about 10% or 1/10, so this is not exact. But this just gives us an idea of when we can start to expect to see that color change. So can I go on to the next slide? So the base to acid ratio is about 1 over 10. And if we go back to the buffer equation, because we now do have a base present and its conjugate acid, so that means that the pH is equal to whatever the pKa of that weak acid is. The indicator, remember, is a weak acid. If it's pKa plus the log of base over acid, which in this case is 1 over 10, if that's true, then we can start to see a color change. What is the log of 1 over 10? You know that one. It's -1. Yeah, that's right. So that term right there is -1. So the pH, whatever the pKa of the indicator is, -1, that pH is where we start to see the color change. Did I hear a bah? Nice, thank you.
Hey, mysterious. Red pass.
Now this only applies when you have an acid that's being titrated with base, because you start with all of this, and then it slowly goes that direction, and so this builds up and that goes down. If you have a base being titrated with an acid, you're going to start with this, and it's going to go back the other way. Because when you have a basing environment, then the base is going to pull all the hydrogens off. Remember, this is an acid, it gives hydrogens to the base. Okay, so the bottom line is this. Can I go to the next slide? All this, just if you're normal, it seems like just mush that's coming out of my mouth. You don't even understand any of it. There is a bottom line, though. I just don't feel right if I just tell you what it is without giving you the background. Okay? That's why I do this. So if you're titrating a base with strong acid, then you're going to get about 10%. You start all conjugate base, and it starts to go that way. When it's a 1 to 10 ratio that way, then this thing has been flipped over. You'll have 10 bases for every 1 acid, and it'll be pKa plus 1. Here's what I need you to know. In general, indicators change color when the pH of their environment is about whatever its pKa is. That's when you can expect to see the color change. So how do we choose a good indicator for a reaction? That's what's written here in blue. Choose an indicator who's going to have a pKa that's close to the pH of the equivalence point. Yes, Andrew?
Can you go back to one slide just for a second?
Yes, no problem. You know what, I'm going to do that just so Andrew you can catch up.
And don't worry, there will be
Is it a stronger weak base?
Doesn't matter. Either way. We don't titrate with weaks, though. We're always going to titrate with strong. So you're going to have a weak acid being titrated with a strong base. I said it doesn't matter before. It does matter. Yeah, you always titrate with strongs.
Get that,
Okay.
Shania? Always titrate with strongs.
She was finger pointing at you, Shania.
I'm wondering if he's strong. Look at that beautiful specimen.
We all good with that? The next slide has some examples of indicators. You don't have to copy this down at all. There is a table in the book that gives info. I'm going to show you that table in a moment. But these go from the strongest acid. Remember, indicators are weak acids. So at the top we have strong acids who are going to change color because they're pKa. This thing, crystal violet, is amazing. Crystal violet has a pKa around 1. So it's pretty strong as an acid. I don't know what the structure that is, what makes it so strong, but so as we go down, they get weaker and weaker and weaker because their pKa's are going up. Remember, the lower the pKa, the stronger the acid is. So whatever the pKa of the acid is, that's the pH that it will indicate a color change for, or that you want it to indicate a color change for. Now, the indicator that we use in our labs, in this class the most, is phenolphthalein. Phenolphthalein is way down here. It's got a pKa of around 9. So that means it's a very weak acid. Why would phenolphthalein work so well? That means that phenolphthalein changes color when the pH is around 9. If we want, like if I have sodium hydroxide being titrated with HCl, or the other way, HCl being titrated with sodium hydroxide, I use phenolphthalein to indicate that. Now, what is the pH when you titrate a strong acid with a strong base? What's the pH of the equivalence point?
7.
It's 7. Why would I use phenolphthalein and not something like bromethymol blue, who that has a pKa close to 7? And that was what the last slide said, is choose an indicator that has a pKa close to the pH of the equivalence point. How come we didn't use this? We used phenolphthalein instead. Anybody want to hazard a guess? Maybe it's economic. Maybe phenolphthalein is cheaper. Maybe. Some of these, I imagine, are very expensive. In general, all indicators are expensive. I mean, I don't know how expensive. It's been a long time since we've ordered these because our stockroom, we've got this big bottle of phenolphthalein, so I don't know how expensive it is to purchase. But we've run out of a lot of these, and we don't replace them, I think, because they're so expensive. But I know we have bromethymol blue. I'll tell you why we use it. First of all, you may think, well, it's not a good idea to use phenolphthalein, but it turns out phenolphthalein is fine, even though the pH is not 7. Here's why. What does the titration curve look like for a strong acid being titrated with a strong base? What does that curve look like? It starts real low, and it gradually goes up, and then does that. Remember that for a strong titration? Okay, so if the equivalence point is right there, is it a big deal if I'm hitting with my indicator right there? No, because that's got a huge vertical jump. Like Shenzi, he's got a real good vertical jump.
Close up on Shenzi.
Good at basketball, Shenzi?
Yeah.
You're built like a basketball player, so
You
that's why I
don't?
said that.
Oh,
You jump high?
used to.
Okay.
Shenzi is not in his prime anymore.
Well, this thing's got the Shenzi jump going on. See, it starts down there real low, and within like a drop or two of the base being added, it jumps almost 10 pH units. So yeah, it's okay if we catch it there rather than there because it's the same drop of NaOH that's noting that that big jump.
As long as it's not going backwards.
Even if it's going backwards, I think hitting it there. What do you mean?
No, with
Compared
the
to
other,
Shenzi?
no, with the other example.
You are just so
Like, remember the
funny.
example on like the one before where the curve went backwards? Yeah.
Oh, the one going back.
These
Yeah,
are
yeah,
the
yeah,
bros.
That's right. Yep. I'm sorry, I forgot that. Okay, now another reason that we use phenolphthalein, and I think phenolphthalein is a superior indicator to almost all of these, is because what is the color change that we're looking for when we use bromethymol blue? When it's in an acid, it's yellow, and when it turns base, it's blue. And I hinted at this when I was talking about the percentage change. When you start to see green, does that mean it's your endpoint? Or when it's a deeper green, does that mean it's your endpoint? It's not easy to see that transition from yellow to blue because you get different shades of green. Which shade is it that gives you the 7 pH? I don't know. So when you have phenolphthalein, it's clear when it's in acid, it's pink when it's in base. The difference between clear and pink is very obvious. I mean, remember doing titrations? You get to a point where, is it pink or not? You hold it up to a sheet of paper and you barely see this little bit of pink, right? Well, if it's pink at all, then you know that it has become basic. And if it's not pink at all, then it's acidic. And if you just barely hit that equivalence point, that means you've just hit it enough base. Remember, it's some percentage base, but that's the best equivalence point that you can get. So anyway, that's why phenolphthalein is good.
That's us, Shania. We hit it every time. Joke.
Does anybody have their homework exercises that they've done over the weekend?
Yeah.
I didn't mean to look at you, Shenzi. I'll look elsewhere. Anybody that's not
Like
a
the
senior have
questions?
homework answers?
Like the questions? I have
The
the
answers to
answers.
them. 57, 59?
Yeah.
Do you have those?
Yeah.
Oh, yeah. I want to show you questions
Not
number
59.
57, 59.
Oh yeah. Those took up like half a page each.
Those were long, I know.
Ooh, Mr. Moore puts a new specimen on the overhead. Ooh. Do-do-do-do. Do-do-do-do.
That's Shannon.
Oh, stop.
Truthy said, that's Shannon.
Will you please look at number 73?
She did them like the first day we got them. Like, I don't even know. This is good.
Okay.
Yeah,
number
Grace.
73. Which of the indicators in the table in the book, I'll show you that table, can be used for exercises 57 and 59? Now let's go back to number 57.
Which of those indicators? I bet you would know, Shemaya.
She probably did these too.
Let's be
Number
true.
57 is right here.
Angela's a hater.
57. Ellen, back here. Number 57
Moore.
is titrating HClO4, a strong acid, with KOH, a strong base. What do you expect to be expect the pH to be at the equivalence point? 7. So which data point is the equivalence point? Looks like 0.008 moles of the acid. So it's going to be 80 m. I believe B is going to be the equivalence point with a pH of 7. Now if we go back to the indicator table right there, this gives us different indicators. Remember, they're weak acid.